Okay, our last section for Chapter 8 is 8.8, and it's improper integrals. And what we're going to see used in this section is all the limit stuff we did in 8.7. All right? So to start with, we call the integral from a to b of f of x dx a definite integral, right? It's a definite integral. And if we don't have the a and the b in there, we call it an indefinite integral. What we're talking about in this section are improper integrals. And improper integrals have one of two things happening. The first thing they may have is that they may have either a positive or a negative or both in place of where the a and the b are. So they don't have an a or a b in one of those locations, maybe both. They have an infinity. Okay? If that's the case, we use limits in order to find the value of these improper integrals. And we just talked in the last section about how we use limits. So that's going to be a helpful feature to remember here. The other case where we have improper integrals is that it will really look like there's an a and a b. I mean, we'll have a 0 and a 7 or something like that. But the problem is that somewhere between that 0 and 7, we have a break in our graph. There's a discontinuity. So we have to break up the integral. So a common one that you have seen before of where a graph breaks is a graph of y equals 1 over x. So if you were finding some sort of an area, say for instance, between -2 and 2, the problem is that at 0, there is no value of your function. So this idea of finding this definite integral is not valid because we've got a break in the graph. So that's the second case. So everybody understand what an improper integral is first. You've either got an infinity on top and bottom or you've got a break in your graph. Okay. So here's our first example. Obviously, this falls into the category number, it's category number 1. Why? Because we see an infinity in there, right? This one actually doesn't, I know it has an x to the 5th in the bottom, but it doesn't have a discontinuity because it doesn't span across the y-axis like that last piece I did, right? It's actually restrained from 1 to infinity. So we've got a graph that actually is continuous. So this is only number 1. So the question asks, determine whether the improper integral, converges or diverges. And then it says, estimate it if it converges. The way they ask the question feels like it's backwards to me. Because the way we're going to decide if it converges or diverges is that we are going to attempt to evaluate it. If we are successful in evaluating it with a number, that is, the answer is 5, it means it converges because it has an answer that's a numerical value. If we attempt to evaluate it and we end up at the end with an answer that's infinity or negative infinity, then that's going to mean that it diverges. So it is by attempting to evaluate it that we are going to make the decision of whether or not it converges or diverges. Okay, so this isn't like a step 1, step 2. It's almost like we're going to do step 2 and then we're going to make that decision about step 1, the way the directions are worded. All right, so all of that aside, here's where things get a little bit different. So you notice you've got this infinity, and that infinity actually makes things a little bit awkward. Because what you would like to do is that you would like to, at some point in here, evaluate this by plugging in the top value and plugging in the bottom value, right? That's a definite integral process. But the problem is we cannot plug in infinity, just like on the last section, right? We don't have infinity as a number, so we don't get to plug it in. So there's a little bit different of a notation that gets involved here because of that infinity. So here's the notation. We have to introduce a limit. We're going to put in the limit. You can call it whatever you like. Your book tends to use b, as b goes to infinity. And we're going to rewrite the integral, and in place of where the infinity was originally, we're going to put the letter b. This is simply notation, okay? We could continue using the infinity later into the problem if we wanted, but eventually we're not going to be able to do this plug-in infinity business, and we're going to have to use limits. So we start out by using the limit notation from the get-go. Everybody good so far? Okay, so we're going to evaluate a limit as our final step of evaluating an antiderivative. So we have from 1 to b. What's a more helpful way to see 3 over x to the 5th written? 3x to the negative 5. That's more helpful for taking an antiderivative, right? So Sorry, see how much space I have. All right, so what's the antiderivative of 3x to the negative 5? Okay, negative 3. I'm thinking we're a little bit off. Let's try again. So the 3 is going to be there, right? And then what's going to happen? What's the antiderivative of x to the negative 5th? There we go. Okay, so the 3 stays put. The antiderivative of x to the negative 5th is x to the negative 4 over negative 4. Is everybody good? Okay. And then with definite integrals, we draw this line and we put the evaluative limits, the ones we want to evaluate them at, on the top and bottom. So now we have b on top, we have 1 on bottom. Notice I rewrote limit, didn't I? And you will too. Okay, so we're going to plug in the letter b. As I plug it in, I'm going to go ahead and move that x to the negative 4th to the denominator as well. I tend to like to see my exponents positive, and that's kind of a mathy thing to do. Most math books will do that as well. So you have this right here with b to the 4th down here. So you have 3 over negative 4 b to the 4th. We have minus, and we have minus the same thing with the number 1 plugged in. So I have 3 over negative 4 times 1 to the 4th. Is that okay? Well, the second piece of that, aside from the fact that it looks funny because there's 2 negatives here, the second piece of that, it's just a number, right? It's not very exciting. I mean, we can find out that value. In fact, you know what value it is. It's the value. Maybe you don't. 3/4, thank you. I knew you did. Yes, it's the value 3/4. The first part is the value that's got the limit part attached to it because it's the part that will either be 0 or infinity, typically speaking. Okay? So what happens in this first part if you attempt to sort of in your mind plug in infinity? So you get a 3 on top. You would actually end up with this idea of infinity on bottom, and then this idea of 3 over infinity is the number 0. It tends towards 0 anyway as x gets infinitely large, or in this case b gets infinitely large. So this first piece becomes 0. The second piece becomes positive 3/4. Okay? The first piece is 0 because of the limiting process. The second piece is 3/4 because I don't have a b value that I need to be evaluating in infinity and so forth, right? So what's my final answer on this? 3/4. So will this converge or diverge? It converges. Does that make sense? It's sort of just this one extra step at the beginning with this limit stuff, and there's that one extra step at the end where I have to evaluate the limit on top of what you've already been working on. All right, let's try another one. All right, so we've got another infinity up there, right, that we're going to be plugging in. But now I have a natural log of x involved. I've got what looks like a product involved, and you guys know there is no product rule for antiderivatives. So you've had lots of different methods in this section about what to do when you have something that looks like a product. What are you going to do for this one? U substitution will actually work, yeah. That's kind of our default. We'd like it to be U substitution. Don't go looking for a substitution by parts or anything like that if you don't have to, right? All right, so if I let this be U substitution, Michaela, you told me that's what you wanted. What would U be?
Natural log x.
Good, natural log of x. So what's du then?
1 over x dx.
1 over x dx, which is actually in my problem, isn't it? Everybody see that okay? All right, excellent. So the first thing I need to do is I need to change this into u's. So this is before I do limits or anything, okay? So as I'm changing this into u's, think about how I wrote this before. Yeah, we might as well. I'm going to leave off, well, you know what, let's do the limit while we do it. That's how I wrote it, that'll work better. All right, so let's do the limit notation here for a moment, and we know that we're going to have that b goes to infinity business. So this is supposed to be from 4 to infinity of the same value, 1 over x natural log of x cubed dx. Oops. Yes, thank you. Okay. All right, let's do our u substitution next then. So I've still already got the limit as b goes to infinity. And anytime I use u substitution, what I do is I leave my limits of integration off. And I know many of you prefer to do that as well. So I'm not actually going to write in those limits of integration until the end again. All right? So as I use u substitution, how will the 1 over 4 times natural log of x cubed dx, what will that turn into? du over u cubed. Or if you prefer, you could write 1 over u cubed with a du at the end. We all good with that? Well, nobody's complaining, so I guess so. All right. What is the antiderivative of 1 over u cubed? Now let me rewrite this one more time this way. Does that look okay? Okay. What is the antiderivative of u to the negative 3? U to the negative 2 over negative 2. And I didn't mention it, but let me mention it now. We don't need plus c's here. Why? Because these are definite integrals. I've got values I'm evaluating them at. Good. All right, so taking a look at this, then I'm going to do one step to rewrite. I didn't do this the last time. We just did it all at one time, but I'm going to do it this time. So this is 1 over negative 2u. Right? Oh, sorry. I left my squared off. Thank you, Chelsea. Yes, u squared. Okay, so I'm supposed to be evaluating this as b goes to infinity, but I need to do something before then. What do I need to do? I need to put those x's back in, right? Because that limit as b goes to infinity was a limit that applied to what x values were happening or what x values we were working with. So this is the limit then as b goes to infinity of 1 over negative 2 natural log of x quantity squared. And I now can evaluate that at the limits I had before, which were b and 4. Any questions? Okay, what's my next step then? One over negative 2 natural log of b squared, then what? Did I get all my pieces in there okay? All right, so we know, of course, that these are going to be positive in a minute here. The issue, though, with whether deciding if it converges or diverges all lies with this piece right here, the part that still has the b in it and the limit part at the beginning. So you need to be thinking about the graph of natural log of x. I know there's a squared and there's a negative 2 over that. I get that. That's fine. But if we're looking for whether it converges or diverges, we can actually talk about that algebraically as well. Do you remember what the graph of natural log of x looks like? It is discontinuous, but not in the interval that we're looking at here. Something like that. It's a little bit flatter than the way mine looks, but do you remember that one? So if we're taking this curve and we're going as x approaches positive infinity, going this direction, what kind of values am I getting on y? They're approaching infinity as well, aren't they? All right. So if I then take an infinity, which is what the natural log of b's value is approaching, and you square it, what happens? That's still getting bigger, so we're still looking at a value that's infinitely large. And then I multiply it by negative 2. It's still infinitely large. It's now negative, but it's still infinitely negative large. I mean, still we're talking about an infinite negative value. It's kind of like our national debt, right? Infinitely negative. So this is an infinite value still here, right, on the denominator. And then what happens when we take the number 1 and we divide it by something that's infinitely large, be it negative or that's 0. So this value at the front here becomes 0. And we have 0 plus 1 over 2 natural log of 4 quantity squared. And there's not a way to simplify that at all. So the answer is actually that second piece. And the other part of the answer is to state, does it converge or diverge? Say that louder for me, Taylor. It converges. And what is the kicker again on making that decision? How do we decide?
A number of things.
If we get a number as our final answer, it converges. If we have something that says infinity, that's when we're going to write diverges down. All right, ready for another one? All right, we have the integral from 0 to 5 of 10 over x. What's different about this one? There's no infinities. What else is different? It's not continuous. Where is it not continuous, Jordan? At 0, right? If I plug in 0 for x, this is 10 over 0, and 10 over 0 is actually a place where we've got an asymptote, right? Or that x equals 0 is an asymptote. So this number 0 at the bottom, although it doesn't look like it's a problem. And so we have to use limits because we don't actually have a value if we were to plug it in. So the first thing we're going to do is we're going to change this to be the limit as b goes to 0, not infinity, but 0, of the integral from b to 5 of 10 over x dx. What is the integral of 10 over x? What is it? Very good. It's 10. Oops, I left my 10 off. 10 ln x. And I'll put the absolute value x here, although I don't really need it. Why do I not need the absolute value? Because it's from 0 to 10, and those are already positive values. I don't know why. Or 0 to 5, rather, and those are already positive values. Okay, is everybody good? So we're going to evaluate this now from 5 down to b. All right, so somebody plug 5 in for me. What do you get? Ten natural log 5. Minus what? 10 natural log b. And like I said, we don't really need the absolute values. They're kind of overkill. All right, I already drew a graph of natural log. It looks something like this, right? So what happens when I plug in 0 here? What part of this graph am I concerned with on this problem? See, on the last problem, I looked as the values went this direction because those are x values that were going towards infinity. But this time, I need to look as x goes towards 0. So as my x values go towards 0 on this graph, what happens to my y values actually? They become negative infinity, don't they? So this is actually, on this one, this is negative infinity. So I actually have 10 ln 5 minus negative infinity. And if you want to be real clear on that, that becomes positive infinity, doesn't it? So this graph has an area that is infinitely large. The area under this graph is infinitely large from 0 to 5. So does it converge or diverge? That diverges. That's the first one of those we did. Is that okay? All right, and I have one more example. This looks almost like the last problem, doesn't it? But what's different? Oh. Change that, please. I changed this after I did this last semester. Obviously, I didn't get the new version updated. Please change it. This will be much more helpful for you to see. So just scratch that out. We're going to have the integral from 1 to infinity of 3 over x. Okay, so identify, looking at this one and looking at the one above this on your page. What are the differences between these two? This one goes to infinity. The last one went to 5. What else? It's not discontinuous, right? This one's actually continuous because I'm not starting at 0. So I'm starting this one at 1. What's the same? The integral is virtually the same, right? I have 3 over x instead of 10 over x, but we recognize that that's pretty much the same graph, right? Okay, so I've actually got limits here like before from 1 to b, and it's 3 over x dx. What's the integral of 3 over x dx? Three ln x. And you can put the absolute values on there if you so desire, but just like on the last one, they don't actually have to be there. All right, what's next? We've still got that limit, right? What do I have? Three natural log of b minus what? 3 natural log of 1. Let's do the 3 natural log of 1 first. What's 3 natural log of 1?
0.
That is 0. What's 3 natural log of b? That's infinity. So I have infinity minus 0. That's infinity. So it diverges. Now, I want you to think about on this one about a graph real quick, and we'll be finished. The graph of this more or less looks like this. So what these two problems in essence have told you is that when you have the value over x, now let me emphasize, this actually doesn't happen if you had x squared. The graph would look virtually the same, but your answers will not be. If you have this over x like you do here, and you include either the part where x is getting close to 0 or the part where x approaches infinity, you have something that does not converge. So if you include either tail end of this graph, you end up with infinite amount of area underneath the curve. And that seems a little bit odd because it seems like that graph just, it's approaching 0. So shouldn't the area somehow stop or get so small that the pieces you're adding don't really matter anymore? And the answer is actually it doesn't work that way when we're dealing with 1 over x. And the reason is because when we graph the natural log of x as the antiderivative, we actually see that going to infinity or going down to negative infinity on either piece of that.